Assalamu alaikum, dear student. Today is the lecture number 1 of week number 4, and in today's lecture the topics we are going to cover are the pressure prism that we have discussed in the previous lecture as well. So this we are going to continue, and second, the pressure on the curved surface. Pressure prism, as we discussed previously, the another technique to find out the pressure on the curved surface, and the first technique what we have discussed is using the formula, and we showed in detail that how we calculate the pressure on the flat surface when the pressure acting on the fluid is hydrostatic, and the pressure acting on the free surface is the atmospheric pressure. So these two conditions are very important to understand. So we apply this technique or the formula when the pressure is hydrostatic pressure and the pressure acting on the free surface is atmospheric pressure. So by using this technique, we use to find out the pressure on the flat surface, as we derived previously, the value of the net resultant force is equal to the volume of the prism, So you see, this is the final equation we derive. The net resultant force acting on the surface, flat surface, the vertical flat surface, is equal to the volume of the prism. This we have derived, and the position of this net resultant force is always h by 3 from the bottom, whatever is the height of the fluid. Okay, so if the height of the fluid is directly started from the flat surface. So now there is another case. If the flat surface is a vertical flat surface is not in contact with the free surface, so this is another way to find out the pressure, because we distribute the pressure distribution in the two profile. One is the uniform pressure distribution and one is the varying pressure distribution. The force exerted due to the uniform pressure distribution is F1, okay, which is acting at the centroid of the flat surface, and other the when the pressure is varying. So in the previous slide we calculated when the pressure is varying, the centroid of the resultant force acting at h by 3 of the height from the bottom, okay, 2 by 3 from the top, or h by 3 from the bottom from the object, not from the free surface. Okay, so here you can see this is the way we can calculate. The F2 is acting at the height 2 by 3 of the 1 by 3 of the height of the object from the bottom. So if you know F1 and F2, this way you can calculate the net resultant force Fr acting on the vertical object. Okay, and the location of the net resultant force you can calculate by using the moment equation acting on the surface. Okay, so this is the equation of the moment equation, and this is how you can find out YR, the location of the net resultant force. Okay, but this is the case when the surface is vertical. This is the case when the surface is vertical. This is the case when the surface is vertical. This is the special case what we have derived previously when theta is equals to 90 degree. So here pressure prism can also be utilized if the flat surface is angular. Okay, so if we know that the pressure distribution will always, the pressure is perpendicular to the surface. So here the pressure is perpendicular to the surface. So this is how you can calculate F1 and F2. This is F1, you can calculate this, you can make it in a 2/2 from here to here if you know this height. Okay, and if you know this height, you can calculate gamma h1 and gamma h2. So make the distribution into 2/2. One is the uniform pressure distribution, and when the other one is varying pressure distribution. Okay, and based on that you can calculate the net resultant force acting on the flat surface and its location as well. So here in solving the pressure prism equation, we assume that the zero surface pressure, because we are considering it is the gauge pressure. In the case of gauge pressure, atmospheric pressure is atmospheric pressure line is a reference point line, and reference we consider as zero. So that's why we are considering a zero surface pressure. Okay, so here we are only considering the pressure due to the fluid, due to the height of the fluid. Okay, there is no atmospheric pressure is included so far. The problem we have solved and the equation we have derived. So when zero surface pressure means we only consider the gauge pressure in the determination of the pressure force, as I said earlier. The following figure includes the atmospheric pressure in the determination of the pressure force. So if we do not ignore the atmospheric pressure, then how it will appear in the pressure distribution form? So if we ignore the atmospheric pressure, it will come like this. But if we do not ignore the atmospheric pressure, the pressure distribution of the atmospheric pressure will appear like this: the pressure due hydrostatic pressure, and this is the pressure due to the atmosphere. So whatever the atmosphere pressure is acting here, the same pressure acting on the other side also. So they are cancelling each other. So the only force which is equal to the net resultant force is the hydrostatic force, the pressure due to the fluid acting on the surface. But in some other cases, okay, so in some other, but if the surface is not free surface, okay, if the surface is not free surface, if it is a closed container, okay, if it is a closed container, let's see, if the surface is not a free surface and the surface is pressurized in a different form, different from atmospheric pressure, for example closed tank, then the magnitude of the hydrostatic force will be different from the one calculated using this equation. Okay, so this is the equation when the free surface, the pressure acting on the free surface is atmospheric pressure. But if the pressure is not atmospheric pressure, see here, this is a closed tank, okay, and this is our gate, okay, this is the gate, and this tank is filled with the oil, and the oil is some distance away from the gate, and it is empty from here, but this is pressurized, and this pressure is acting on the whole surface, and this pressure is equal to 50 kilopascal. We'll see in the so this is the meaning that when the pressure is other than the atmospheric pressure, we cannot ignore that, okay, that pressure has to be considered. So let's solve this example and see how we solve this problem. Okay, so this is the case when the pressure acting on the surface is not atmospheric, it is other than the atmospheric pressure. If the pressure is atmospheric, we have many ways to solve the problem, as this one, and this is the problem. This is the equation we have. This is the equation we have solved. Okay, this is the formula that we derive to find out the net resultant force acting on the flat surface, okay, underwater, okay, but when the case is pressure on the free surface is atmospheric pressure. Okay, so now when the pressure is not atmospheric pressure, then how we can solve it? Let's say a pressurized tank oil, the specific gravity is given and has a square 0.6 meter by 6 meter plate bolted to its side. This is 0.6 meter by 6 meter bolted plate, and this plate is basically openable. Okay, this is not part of the continuous part of the tank. Okay, as illustrated in the figure, when the pressure gauge on the top of the tank reads 50 kilopascal, what is the magnitude and location of the resultant force on the attached plate? Okay, the outside of the tank is at atmospheric pressure. Outside is the pressure is atmospheric pressure, inside is the pressure is not atmospheric pressure. Okay, is the pressure different than the atmospheric pressure? So whatever the atmospheric pressure is acting here, the same pressure is acting here, so they are going to be cancel each other. So now we are making a pressure distribution profile acting on the flat surface. So we are considering this bolted plate as a flat surface, and now consider this is the oil surface. Okay, and the pressure on this oil surface is, consider this pressure is PS. Okay, so that is PS, that is going to be a 50 kilopascal. Okay, and gamma H1, this is the height of the fluid above the gate. So this is the height of the fluid above the gate, the gamma H1 from here to here, and this is the pressure distribution. Okay, starting from the plate. Okay, it is gradually increasing. So that means three kind of pressure we have here now. One is the pressurized surface pressure, other is the hydrostatic pressure above the plate, and the fluid at the fluid pressure at the plate. Okay, so from here to here you can see the pressure is uniform. Okay, this pressure is due to the pressurized pressure on the surface and pressure due to the fluid above the flat plate. Okay, so F1, since the pressure is uniform, so the location, the position where the F1 is acting is the centroid of the flat plate. So what is the centroid of this flat plate? Is the middle of the plate. So F1 is acting at the middle of the plate, and F1, the magnitude, going to be equal to PS plus gamma H1. Okay, and this is rectangle. Okay, if it is rectangle, so we know it is equal to half the volume of the prism, half the volume of the prism. Okay, that we derived previously. Okay, so this is how we can, so this pressure will give you F2. Okay, and then if we sum up F1 and F2, we can calculate FR, and let's see. So see here, F1 is equals to PS gamma H1 into area, that we know that pressure multiplied by the area will give you the force. So this is how we get the force F1. Second, F2 will be equal to gamma HCA. This is very obvious. Okay, so this is the varying pressure distribution, and F2 will be equal to what? HC, okay, into A, gamma, the density of the fluid, into HC into A. What is HC? HC, we know that in the case it is 1/3 of the height of the prism. So 1/3 of the height of the prism, the height of the prism is 0.6. It is divided by 3, so we will end up with 0.2. So this is the location of F2, and the magnitude of F2 is going to be HC into gamma into HC into A. So this is the 0.9 is the specific gravity, the water density, into 0.6/2. The HC, it is always height from the centroid. Okay, and this is the area of the prism. So here, this is the location of F2. This is the position of F2 where it is acting. The centroid is definitely at the center. Okay, so this is how we calculated F2. Now we know that F1 and F2, and we can calculate the net resultant force is going to be F1 plus F2 will give you the net resultant force. Now we are going to find out the location of F2. Where is the location of FR? Where is the location of FR? FR is this is the position which is at the distance of y0 from the bottom. So let's apply the moment. So to calculate the position, let's apply the moment. So the vertical location of FR can be obtained by summing the moment around around an axis through point O, so that, so this is point O, take the moment along this axis. So all the distances are known from here to here except y0, and all the forces are known including Fr, F1 and F2. So based on that we will take the moment, and when we will simplify it we will end up with y0 is equals to 0.296 meters. So this is the end of the hydrostatic force on the flat surfaces. Now we are going to move to the same topic but little different, the hydrostatic force on a curved surface. If the surface is not flat, as we discussed previously, if it is flat it is very easy. We know two different techniques to find out the flat surface pressure acting on the flat surface. But if the surface is curved, okay, and where we observe such surfaces, the curved surfaces occur in many structures, that is dams, cross section of circular pipes or tanks. If a surface is curved, okay, then how we can calculate the hydrostatic force acting on the curved surface, how we can calculate the net resultant force acting on the curved surface. So if the surface is curved, the forces produced by fluid pressure will not be parallel but rather concentric or radial. Okay, so definitely we know that the pressure always acting perpendicular to the surface. The pressure will act like this, okay. Their direction and magnitude will change from point to point on the curved surface, okay. So this is the difference, okay, this is the difference. The easiest way to determine the resultant hydrostatic force Fr acting on the two-dimensional curved surface BC. So consider this is a BC curve, okay, this is the BC curve. If you want to find out the net resultant force acting on this curve, so what is the best way to do it? The horizontal and vertical component of FH and FV, okay, so that the tank exerts on the fluid separately, because you see FH and FV are the reactive force, okay. Let's move on to the next slide. Okay, this is the reactive force by the tank on the fluid. So if we can calculate these two reactive force, we can easily calculate the net resultant force acting on the fluid. Okay, here you can see since this surface is curved, so the forces, the pressure force are acting perpendicular to the surface. As the surface is changing, the direction of the pressure is also changing, but all the forces are passing through the center of the curvature or center of the curve. All the pressure force are passing through the center of the curved surface, okay. So now this is done by considering the free body diagram ABC, the liquid block enclosed by the curved surface and the two plane surfaces, okay, one horizontal and one vertical. So we make a fluid block, okay. So one is horizontal plane, one is vertical plane, and one is the curved surface we have, okay, and these two planes are passing through the center of the curve, okay. Note that the vertical surface AC, this is the vertical surface AC of the liquid block, is simply the projection of the curved surface on a vertical plane. So this AC is basically the projection. So if you are seeing from here, so what projection you will see? You will see this is the projection of vertical at vertical plane, okay. This is the, if you are seeing from here, so this is the projection, and this projection is basically AC. In the same way, okay, and the horizontal surface AB. This horizontal surface AB is the projection of the curved surface on the horizontal plane. So this is the horizontal plane you are seeing from here. If you are seeing from here, so what is the projection of BC? The projection of BC will be equal to AB. This is going to be flat like this. Okay, so the projection of this curved surface is AB. Okay, so the resultant force acting on the curved solid surface is then equal and opposite to the force acting on the curved liquid surface. Okay, so whatever is the force acting by the fluid on the surface is equal to the opposing force by the tank surface or by the curved surface. So according to Newton's third law, okay, according to Newton's third law, the force acting in x direction and force acting in y direction. Okay, so this is a free body diagram. Okay, this is, you see, this is the vertical projection, this is the horizontal projection of the curved surface. So how we solve the problem of the curved surface? We make the fluid block, okay, like this, ABC. We take a block, we take the projections in horizontal and vertical direction. Wherever the point is meeting, that is basically the center of the curved surface, and we consider this is a horizontal plane and this is the vertical plane. So take a free body diagram. The reactive force Fv in vertical direction, the reactive force in the vertical direction. This is the horizontal surface where the active force is FAC by the fluid. This is by the fluid, this is by the fluid, and W is also by the fluid. And the acting force by the fluid on the curved surface is FEB in the horizontal direction and FAC in the vertical direction, and also due to the weight of the fluid that is acting vertically downward. Okay, so this is a free body diagram. We have mentioned all the forces acting on the plane. So now apply the force balance equation in the horizontal direction and in the vertical direction. So let's see, in the horizontal direction, FH is minus FEC equals to 0 because we have only two forces. Okay, so that is FH is equals to FAC. And how we can calculate FAC? So consider this is a vertical flat plate. Okay, this is acting like a vertical flat plate. Okay, so how the forces are acting on this surface? Definitely the forces are varying. Okay, the forces are not uniform here, the forces are varying. So in that case, F is equals to gamma hc into AC. What is AC? Distance from the centroid to the free surface, from here to free surface. Okay, and AC is the area. That we can easily know that what area AC. So if we know the density of the fluid, if we know HC, if we know area, we can easily calculate the FH. Okay, now the other component, the force acting in the vertical direction. Okay, so FV is minus W because this is FV in the vertical direction considering positive. W is acting downward, FAC is acting downward, equal to 0. So FV will be equal to W plus FAC. Okay, so these two forces are acting on this projection of the curved surface. So this what is the weight of the fluid is specific weight into volume plus FAC. This is a surface where the pressure is uniform. Okay, this is the flat plate where the pressure is uniform. So it's very simple. This is basically the gamma H into AB. So H is equals to the height of the fluid, or it's very simple. Okay, from the free surface to the height into AB. Okay, so by this way we can say that weight of the fluid supported by the curved surface up to the free surface. If you know FH and FV, you can easily calculate the net resultant force acting on the curved surface by using this formula, okay, by using a Pythagoras theorem. Fr is equals to under root FH square plus FV square. This will give you the net resultant force, and if you know the horizontal and vertical component, you can find out the position of the net resultant force also from the vertical axis. So this is the theta that will give you position of the net resultant force, which is always passing through the center of the curve. So here the magnitude of the resultant force is obtained by using this equation, and the angle theta can be observed by using this equation, okay. So here you can see this theta is from the vertical side, not from the horizontal side, keep in mind. An inspection of this result will show that the line of action of the resultant force passing through the center of the curve, because always the pressure force is acting perpendicular to the surface, or whatever is the position, but it will always perpendicular to the surface and passing through the origin of the curved surface. Okay, so this is not a surprising result, since each point on the curved surface, the element force due to pressure is normal to the surface, and each line of action must pass through the center of the curve. Okay, so now let's move on to some practice problem. Consider a 4-meter long curve. Consider a 4-meter long curve. This curve is 4 meter long in this direction, in the 3D. If you see in the 3 direction, so this is long in this direction, okay. Long curve gate is located in the side of a reservoir containing water as shown in figure. The magnitude of the horizontal and vertical component determine the magnitude of the horizontal and vertical component of the force of water on the gate. Will this force pass through point A? And we have to say this force will pass through the center of the curve or not. Okay, so some informations are given. From the height of the fluid are 9 meter. Okay, the radius of the curved surface is 3 meter is given. Okay, and the width, okay, and the length of the gate is also given in the 3D direction. If you see, so this is in this direction, okay, in the Z direction, the width is the length is 4 meter. So now what is our first step? First step is to make a free body diagram. So we will take a horizontal line from the end of the curve in the horizontal direction, and one in the vertical direction. So these two lines will end up at the point A, and then we make a free body diagram. So this is the free body diagram. Okay, this is the point A, and the force acting in the horizontal plane is F1, and force acting due to the fluid is F1 in the horizontal direction, and force acting due to the fluid on the plane is F2 in the vertical direction, and FH and FE are the reactive force due to the curve, given by the curve, and W is the weight of the fluid. Okay, so sigma, so this is x direction and this is y direction. We considered the net force acting on the x direction is equal to FH into F2. F2 is equals to gamma into HC into A2. Okay, so gamma is the density of the fluid. Okay, what is HC? HC is the height from the centroid to the free surface. So you can see this is 9 meter and this is 3 meter. So this is going to be 6 meter from the top of the curve, and centroid is half. Okay, this is your flat plate. Okay, this is your flat plate, and the center of the flat plate is 1.5 meter. So here 6 meter plus 1.5 meter, and the area of the curve. What is the area? This is the curve. So what is this? This is the radius is 3 meter into what is the area of this flat surface. Okay, so this is 3 and the length is 4 meter is given. Okay, so the area is 3 into 4 meter, because right now we are not considering this, we are considering these this is the surface and this is the surface. Okay, so this is 3 meter into this is 4 is the length of the curved surface. So this way we can calculate the force acting in the horizontal direction, that is 882 kilonewton. Okay, now next, the force acting in the y direction. The force acting in the y direction are, okay, F1, okay, is the downward direction. This is positive vertical direction. Fv gonna be equal to this. Fv is balanced the two forces which is acting in the downward direction. So Fv is equals to F1 plus weight of the fluid. Okay, so here what is F1? F1 is equals to this is the flat surface. Okay, this is the flat surface, and gamma is the density of the fluid, and hc from here is 6 meter. Okay, so this is 6 meter, you can see from here, because this is our flat surface at this point, and height from here is 6 meter because this 3 meter is the radius of the curve. Okay, so 9 minus 3 is equal to 6. So 6, then length of, then the area of the plane, 3 into 4 meter. Okay, this will give you F1. Now W, the weight of the fluid. So what is the weight of the fluid? The total weight. Okay, the weight, this is the volume we will consider. Okay, this is the volume of the fluid which is acting on the surface. Okay, this is the volume of the fluid which is acting on the curved surface. So what is the weight? Weight is equals to weight density into volume. So weight density of the water, if the fluid is water, so it is 9.80 kilonewton per meter square. Now the area, how we can calculate the area? So this is basically the quarter circle. So what is the area of the circle? Is pi by 4 pi r square. Okay, what is the area? Area is equals to area of the circle is pi r square, or pi d square by 4. Okay, so if you divide by 4, you can get this quarter area. Okay, so you can get this quarter area multiplied by the length is 4 meter. So if you multiply with the 4 meter, you will end up with 9 pi meter cube. Okay, you can see, you will solve it, you will see. So what I'm saying, you can see here, pi r square by 4. Okay, this will give you the pi r square will give you the area of a circle. Divide by 4, this will give you the area of the quarter circle. Multiplied by 4, the length will give you the total volume of this quarter circle, and that is going to be equal to 9 pi. So 9 pi I put it here. So this way I calculated the F1 and W, and when I add those values here in FV, so FV is going to be equal to 983 kilonewton. Okay, so now if I add FV and F1, I will get the net resultant force. The direction of all differential forces acting on the curved surface is perpendicular to surface, and therefore the resultant must pass through the intersection of all these force which is at a point A. As I told you earlier, because according to the law, the force pressure is always acting perpendicular to the surface. So as the surface is changing, the direction of the force is also changing. So all the forces must pass through this point A. Now let's move on to the another problem, and there is some more thing to understand and some new things you will learn here. So let's see here. The problem is a long solid cylinder of radius point A. Okay, this is a long solid cylinder. Okay, this is a cylinder. Okay, this is a solid. R is equals to 0.8 meter, hinged at point A. It is hinged, it is movable from this point, is used as an automatic gate. Okay, as shown in figure 3.6. Since it is movable, so we are considering it is automatic. When the water level reaches 5 meter, okay, when the water level reaches 5 meter, the gate opens by turning about the hinge at point A. Okay, when the level is reaches as 5 meter, the gate is about to move. It doesn't move, but if it moves just little bit above 5 meter, 5.001 or 5.1 or 5.01 meter, okay, the hinge will move slightly, okay, but at the 5 meter it is just about to move, okay, so it is not moving but it is about to move, okay. That means the net reacting force acting by the cylinder to the fluid is equal, okay. So determine the hydrostatic force acting on the cylinder. So we have to find out the hydrostatic force, because this is the curved surface, you can see this is the curved surface, so we have to find out the hydrostatic force acting on the cylinder and its line of action when the gate opens, okay, and we have to find out the line of action of the resultant force. Second, the weight of the cylinder per meter length of the cylinder. So we have to find out the weight of the cylinder per meter length of the cylinder. So we don't know the length, but per meter length we can find out the weight of the cylinder. So here you can see the pressure distribution on this curved surface. You see the curve is not holding any fluid. The curve which is holding the fluid is acting force on the fluid, okay, the fluid is force on the fluid. So what is the force acting downward, or what is the fluid which is acting downward? So that this is, you can see this is the curve, okay, and here is the fluid pressure distribution, okay. This is, you can see I made it, this is our curved surface, and I take the projection in the horizontal direction and I took the projection in the vertical direction. So this is the projection in the vertical direction and this is the projection in the horizontal direction, because this is the curved surface, and if you see from here, so this is the projection you will see, and if you see from the horizontal direction, this is the projection you will see, this is the projection you will see from the bottom. Here is the varying and here is the uniform pressure distribution, and this is the reactive force due to the curved surface. What is the reactive force? Fv and Fh, and this is the resultant force that we have to find out. So the very simple, so here is the this is the vertical surface, okay, the gamma h we can easily find out, and this is the flat surface, okay, this is very simple to find out. So Fh is equals to Fx, the force which is acting in the horizontal direction, okay, that is Fh is going to be equal to, so what is Fh? So this is basically the Fh, okay, so Fh is equals to pressure into area. What is the pressure? Gamma g into hc into a. What is hc? Hc is equals to height of the fluid. This is from here to here is 4.2 meter, and then the centroid of this, what is the height? 0.8. So centroid will be equal to 0.8, okay, the centroid will be equal to, centroid of this surface will be equal to 0.2 by 4, okay, so this is 0.8 by 2, that means 0.4. So this is going to be 4.2 plus 0.4, and this is the area. I am considering that the length of the cylinder is 1 meter, so this 1 meter is going to be length. So this is how we will calculate the Fh, and Fy will be equal to Fy minus W. How? You can see the force is acting vertically downward, okay, the reactive force is acting like the reactive force is acting from here, okay, and the vertical force is exerting pressure from the bottom, from here, you see, not from the top. The force is exerting from the bottom, okay, from here, not from the top. So that's why Fy is acting vertically upward, and Fv is acting vertically downward, okay. So because the fluid, this fluid is putting a pressure on it, okay, and this is the reactive force. So sigma y is equals to sigma y, yani Fv gonna be equal to Fy minus W, because this is vertically upward, this is vertically downward. So Fv is equals to Fy minus W. So vertical force going to be equal to equal to like this, and weight of the fluid, this is very important to understand, the weight of the fluid. So what is the weight of the fluid? This we have to find out this weight of the fluid. So how we can find out this weight of the fluid? So you can see this is the only fluid which is putting pressure on this surface. Okay, so we are considering this is a square 0.8 0.8. So this 0.8 into 0.8 is giving you a square, and we need this area, we need this volume or this area. Okay, so this square is including this quarter circle as well as this area. So we are going to consider this area minus this quarter circle. So what we can do, 0.8 minus this circle. Okay, this is going to be what? This is going to be 0.8 into 0.8 minus what? Minus this quarter circle. What is the area of the circle? We can see here. Okay, r square, that is rectangle, that is square, minus pi r square by 4 into 1 meter is the length of the cylinder. So this will give you the volume of the water. Okay, this is how you can find out the weight of the fluid, which is basically touching with the curved surface or making a projection. Okay, and then take the net resultant force and find out the theta. Okay, so this is how we can find out the net resultant force and the direction of the force. Okay, so now the second part, when the water level is 5 meter high, the gate is about to open. As I told you in the starting of the problem, is about to open means the net reactive force and the active force are equal. Okay, the net reactive force is 0. If you increase just a little bit level of the water higher, the water will start flowing. Okay, the cylinder will not be able to stop the fluid. So that means the reactive forces at this condition will be 0. Okay, so when the water level is 5 meter high, the gate is about to open. That means the reactive forces applied due to the cylinder is going to be 0. So the net forces acting due to the fluid is equal to this. Okay, so that means the net active and reactive force at this condition will be equal to 0. So this is the active force and this is the reactive force by the cylinder. So we have to find out the weight of the cylinder. So weight of the cylinder is going to be Fr sine theta. This is, both are known. So this is the weight of the cylinder per meter length. Okay, this we can find out. So now the next lecture, in the next lecture we will start the buoyancy and other buoyancy related topics. So for today, it's our lecture is complete. Assalamu alaikum.